The landscape of Flixborough, England, on the afternoon of 1st June 1974, looked like a battlefield. Where a large chemical plant once stood, there was now only twisted metal and smoking rubble. An enormous explosion had just occurred. The blast was so powerful it was heard miles away. It flattened the entire industrial site. Buildings were reduced to their foundations. Heavy steel structures were bent and torn as if they were made of paper. Vehicles were tossed and mangled, scattered across the devastated grounds. The force of the explosion had ripped the heart out of the factory, leaving a scene of total destruction under a hazy, chemical-filled sky. From the air, the scale of the catastrophe was even more apparent. Aerial photographs showed a vast circle of ruin. The central processing area was completely gone. What remained was a crater and a collection of debris. The administrative building, located some distance from the main plant, had its roof torn off and its walls collapsed. Windows in houses and shops in nearby villages were shattered. The shockwave had traveled far, a physical testament to the immense energy released. For those on the ground, the initial moments were chaos and disbelief. A slow, grim search for survivors began amidst the wreckage, a task made difficult by the sheer extent of the damage. This was not an act of war. This was an industrial accident. The Nypro chemical works had, in a single moment, ceased to exist. The explosion claimed the lives of 28 people working at the site that Saturday afternoon. It injured many more, both on and off the site. The disaster was a profound shock to the nation and the global chemical industry. It raised terrifying questions about the safety of modern industrial processes. How could a modern facility, built with advanced technology and engineering, fail so completely and so violently? The Nypro plant at Flixborough was a key part of the United Kingdom's chemical industry. The Nypro plant at Flixborough, its primary purpose was to produce a chemical called caprolactam. Caprolactam is the essential raw material used to manufacture Nylon 6. Carpets, clothing, car parts, industrial fabrics. The plant was a complex network of pipes, vessels, and reactors. The process began with a common industrial chemical, cyclohexane. Cyclohexane was the feedstock, the starting point for the entire operation. It was a flammable liquid, similar to petrol, which required careful handling. The core of the process involved 6 large steel vessels called reactors. These reactors were arranged in a series like a train. Cyclohexane was pumped into the first reactor and then flowed sequentially through the other 5. Inside these reactors, the cyclohexane was subjected to high temperature and high pressure. The temperature was maintained at approximately 155 degrees Celsius. The pressure was kept at around 8.6 bar, or about 8 times normal atmospheric pressure. These harsh conditions were necessary to force the cyclohexane to react with air and oxidize. This was a continuous process, running 24 hours a day. The reactors themselves were large and robust pieces of equipment. Each one was a vertical cylinder made of mild steel, with a stainless steel lining to resist corrosion from the chemicals inside. They were connected by a series of 28-inch diameter pipes, allowing the hot pressurized cyclohexane to flow from one vessel to the next. The system was designed to contain this volatile chemical safely under its operating conditions. It included various instruments to monitor pressure and temperature, along with safety valves designed to release excess pressure in an emergency. The entire setup was a feat of chemical engineering, designed for high-volume, efficient production. However, the nature of the process meant that it held inherent dangers. The plant contained a huge inventory of cyclohexane, a highly flammable substance. Keeping this substance contained at high pressure and temperature was the most critical safety function of the entire facility. Any breach in the integrity of the reactors or the connecting pipework would lead to a massive and rapid release of this hazardous material. The energy contained within the pressurized system was immense. A loss of containment would not just be a leak. It would be an explosive release of hot vaporizing liquid, a scenario that process engineers are trained to prevent at all costs. In late March 1974, several weeks before the disaster, a problem emerged. Workers at the plant discovered a leak of cyclohexane from Reactor 5, one of the 6 vessels in the series. After cooling the reactor down and inspecting it, they found a serious issue. A vertical 6-foot-long crack had formed in the mild steel shell of the reactor. This was a grave discovery. A crack in a high-pressure vessel is a fundamental failure of its structural integrity. The reactor was no longer safe to operate. Plant management was faced with a critical decision: what to do about the damaged vessel, while they investigated the cause of the cracking and waited for a replacement. The most straightforward and safest option would have been to shut down the entire plant. That would have allowed for a thorough investigation without ongoing risk. However, shutting down meant stopping production of caprolactam. That would have significant commercial consequences for the company. Management was under pressure to keep the plant running and maintain output. Therefore, they sought an alternative solution. They decided to remove the faulty reactor 5 from the process line entirely. The plan was to physically bypass it, allowing the other 5 reactors to continue operating, albeit at reduced capacity. This decision led to the fabrication of a temporary bypass assembly. The idea was to connect the outlet of reactor 4 directly to the inlet of reactor 6, creating a shortcut around the empty space where reactor 5 used to be. This required a custom-built piece of pipework. The gap was large. The inlets and outlets of the reactors were not perfectly aligned. There was a drop in height between them. A simple straight pipe would not work. The solution they devised was to construct a dogleg-shaped pipe to bridge the 28-inch diameter openings. This bypass pipe would have to perform the same duty as the original pipework, containing hot, pressurized cyclohexane. The decision to install this bypass was made quickly. The plant's works engineer had left his position and had not yet been replaced. This meant there was no single, qualified mechanical engineer on site with the authority to oversee such a critical modification. The responsibility fell to a group of managers, none of whom were professional mechanical engineers. They proceeded with the plan to keep the plant online. They believed this temporary fix was a reasonable and practical way to solve their operational problem. They did not conduct a formal safety review or a detailed engineering analysis of the proposed modification. The focus was on getting the plant back up and running as soon as possible. The design and installation of the bypass pipe were fundamentally flawed. The piece was fabricated in the plant's own workshop. It was constructed from a straight piece of 20-inch diameter pipe, smaller than the 28-inch nozzles on the reactors it was meant to connect. This pipe was then welded to 2 bellows, flexible metal components, that happened to be the correct 28-inch diameter. This assembly was bolted into the gap between reactor 4 and reactor 6. The entire process was rushed. Crucially, no formal engineering drawings were made for the temporary pipe. No qualified designer checked the concept. The lack of proper engineering oversight had severe consequences. The bypass pipe was not designed to withstand operational forces. No calculations were performed to assess stresses on the pipe, especially the complex angled dogleg shape. The internal pressure of the cyclohexane would create a powerful thrust force trying to push the pipe apart. The bellows were designed to absorb axial expansion and contraction. They were not intended to withstand the shearing forces from the dogleg geometry. The assembly was a makeshift contrivance, not a properly engineered component. Furthermore, the bypass pipe was inadequately supported. The original robust pipework had proper supports designed to carry weight and resist operational forces. The temporary pipe was supported by simple scaffolding, not designed for this purpose. The scaffolding could not restrain the pipe or stop it from squirming and twisting under pressure. The weight plus immense internal pressure placed the assembly under complex, dangerous stresses that it was never designed to handle. It was an accident waiting to happen from the moment it was installed. The decision-making process itself was a critical failure. The modification was treated as a simple plumbing job, a minor repair. In reality, it was a major change to the design and integrity of a high-hazard process system. Standard engineering practice would have demanded a formal design review, stress calculations by a competent engineer, a pressure test of the new component before installation, a systematic review of all potential risks. None of these essential safety checks were performed. The team made a judgment based on experience but lacked the specific mechanical design expertise required. The bypass was, in engineering terms, dangerously unstable. On the afternoon of Saturday, the 1st of June 1974, the plant was restarting after a separate technical issue. As the system was brought back up to normal temperature and pressure, the flawed bypass pipe failed. Intense internal pressure and thermal expansion caused the dogleg pipe to rupture violently. The two bellows at either end tore apart. Two massive 28-inch holes opened in the high-pressure system. Huge quantities of hot pressurized cyclohexane blasted out in seconds. It was a catastrophic loss of containment. The release was immense and incredibly fast. An estimated 30 tons of cyclohexane erupted from the broken pipework. Under high pressure and well above its boiling point, the liquid instantly flashed into vapor and liquid droplets. That formed a massive, dense, highly flammable cloud. The cloud was heavier than air and slumped, spreading outwards across the plant. It flowed over the ground and around buildings, covering several hundred meters in diameter. Within less than a minute, a huge volume of the factory was enveloped in an explosive cyclohexane air mixture. All that was needed was a source of ignition. In a large operating complex, ignition sources are everywhere. An electrical spark from a motor, the flame from a furnace in a nearby hydrogen plant, or the exhaust from a vehicle. The exact source was never definitively identified, but it did not matter. The vapor cloud found a spark. The result, a devastating vapor cloud explosion, a VCE. The entire cloud detonated in a single massive blast, releasing energy equivalent to an estimated 16 tons of TNT. The explosion utterly destroyed the Flixborough plant. A massive fireball rose into the air, and a powerful blast wave radiated outwards, flattening everything in its path. The main control room collapsed, killing everyone inside. Structures across the site were destroyed, and the nearby village of Flixborough was heavily damaged. 28 people lost their lives. 36 other workers suffered serious injuries. The event stands as one of the worst industrial accidents in British history, the direct result of the rupture of one temporary pipe. The official Court of Inquiry, established to investigate the disaster, concluded that the cause was clear and direct. The explosion was the direct result of the failure of the makeshift bypass assembly. The inquiry report said the bypass had no proper design study, nor was it properly tested. The decision to install it came from people who didn't fully understand the engineering, the complex principles involved, the behavior of bellows, the stresses in a dogleg pipe under pressure. The report was a damning indictment of engineering and management practices. The investigation showed a profound organizational failure. The plant lacked a systematic process for managing changes to equipment and procedures. The bypass installation was a significant modification, but it was treated like routine maintenance. There was no formal risk assessment. There was no requirement for a qualified mechanical engineer to sign off. The inquiry made it painfully clear a culture had developed prioritizing production over safety engineering. That lack of control was identified as the root cause. This became known as management of change. Flixborough was a watershed moment. It sent shockwaves through regulators worldwide, forcing a complete rethinking of safety in high-hazard industries. The final report led directly to new UK legislation, the Health and Safety at Work, etc. Act 1974, placing greater responsibility on employers to ensure safe operations. In the United States, Flixborough influenced development of OSHA's Process Safety Management Standard. In Europe, it spurred the Seveso directives. The legacy is the modern framework of process safety. The framework insists on multiple layers of protection. It requires companies to conduct detailed hazard and operability studies, HAZOPs, to identify potential risks before they occur. It mandates that all changes, however small or temporary, go through a formal management of change procedure. This includes engineering checks, risk assessments, formal authorization. The disaster taught leaders a simple, powerful lesson. Small, uncontrolled changes can bypass all defenses and lead to the worst outcome. Safety is not a matter of luck, it is a matter of discipline.